Okay, so using the ideal equation of state, which is otherwise known as the ideal gas law, PV equals nRT. So just remember the pressure should be in atmospheres, the volume should be in liters, N is the number of moles of gas, so in moles, the gas constant is 0.08206 uh, liter atmospheres per mole per Kelvin, and your temperature will be in Kelvin, okay? So in terms of dimensional analysis, hopefully you guys can see that everything should cancel. Okay, so liters on both sides, atmospheres on both sides, moles and Kelvin. Okay, so we can check that we're using the right version of the gas constant by dimensional analysis. As a little aside, occasionally you may come across pressure in pascals and volume in meters cubed, and this would be the one time that you would actually use the other version of the gas constant, because at 8.314 joules per mole per Kelvin, okay, well, the SI unit joule is kilogram meters squared per second squared, and a Pascal is, well, force over area, so Newton meters squared per meter squared, so that'll be kilogram meters to the -1 per second squared. If I could write an S, that'd be useful. So if you actually have your pressure in Pascal, so that'd be kilogram meters to the -1, seconds to the -2, times your volume in meters cubed, okay, equals N, well, that's still going to be in moles, times your other gas constant, 8.314 joules, which is kilograms meter squared per second squared, kilogram meter squared per second squared, per mole per Kelvin, so mole to the -1, Kelvin to the -1, and then your temperature is going to be in Kelvin. As you can see, all these units will cancel out correctly as well. So obviously moles in Kelvin cancel out, and look at the kilograms, meters to the -1 plus meters cubed is meters squared, so that will cancel here, and seconds to the -2, seconds to the -2. So that is if your pressure is in pascals and your volume is in meters cubed. That's the only time you'd use the other version of the gas constant, okay? So it doesn't come up that often, but I thought you just want to know. So we've been given the temperature. Temperature has to be in Kelvin, okay? So 15 degrees Celsius plus 273.15 would help if I could type. Will give me my temperature in Kelvin, so that is 288.15 Kelvin for my temperature. And my 453 millimoles, well, now it's going to be in moles, so 453 millimoles. You can use SI unit conversion, that 1 millimole equals 10 to the power of 3 moles. That's what the milli prefix means. So then I can take that 453 millimole and use that equivalency as a unit conversion factor. So millimole on the bottom, moles on the top. So I know that 1 millimole is 10 to the power of 3 moles. Hang on, I've done that wrong entirely. Milli is to the -3. Why did I write to the 3? Milli is 10 to the -3. So why did I write that there? I don't know, to be honest. I'll put a little, because kilo is 10 to the +3. All right, so our millimoles should cancel out. So therefore we have 0.453 moles. So in our PV equals nRT, we have N, R is a constant, we have T, and we've been given pressure in the question as well. Look here, we've got our pressure of 1 atmosphere. So we are rearranging and solving for volume. Okay, so how do we do that? Volume equals nRT over P is what we are going to do. So then my volume is going to be my number of moles, 0.453 moles, times the gas constant, okay, because I've got the pressure in atmospheres, and my volume is going to come out in liters if I use the 0.08206 version of the gas constant, that's going to be fine. Litre atmospheres per mole per Kelvin. My temperature in Kelvin is 288.15 Kelvin. Are you going to fit on one line, or do I have to take you somewhere else? I'm going to take you over here. Okay. And then divide by the pressure, which is 1 atmosphere. Always check that your units are cancelling correctly. So that's how you can verify you've used the right version of the gas constant and done everything right. So atmospheres cancels, moles cancels, Kelvin cancels, leaving me with units of litres, which is very appropriate for a volume. All right, so 0.453 moles would help if I could type that incorrectly, times 0.08206 times 288.15 Kelvin divided by 1 atmosphere gives me 10.7 litres to 3 significant digits. Okay, so I'd like to do one where we actually use the other version of the gas constant just to show how that works, okay? And I found an example, and there is also going to be lots of tasty dimensional analysis in here. So this is like literally as hard as it can get, okay? So notice we've been given the fact that the vessel is a stainless steel cylinder, so we don't even get given the volume. We've got to work it out ourselves, which is incredibly harsh, okay? So the volume is going to be pi r squared h for a cylinder, and r is the radius. This is just every aspect of this question is just awful. So you're really going to work for it today because you've only been given the diameter. So the radius is half of the diameter. So what we're going to have to do is pi times 35.0 centimeters over 2. And that is going to be squared. And then times h, which is 42 centimeters. So that is going to give us a volume in centimeters cubed. So it's not even in meters cubed. And this is typically the kind of unit conversion that I have found students find kind of tricky. And I'm looking down because I'm trying to find my pi button on my calculator. It's been that long. Where is my pi button? That's fun, isn't it? Shift pi, where are you? This is why it's important to practice with your calculator before an exam. Okay, so pi times 35 over 2 squared times 42 gives me 4 times 10 to the power of 4 centimeters cubed. I'm just going to put a few decimal places. 4.0408.7. So let's call that 9 times 10 to the power of 1, 2, 3, 4 centimeters squared. Okay, so even if you have your conversion between centimeters and meters, don't forget whenever, not squared, cubed, because we've times by 2. You have to be really careful because we know that 1 centimeter is 10 to the minus 1 meters, okay, because there's 10 to the minus 2 meters. I'm thinking of decimeters because there's 100 centimeters in a meter, right? But whenever it is cubed, you've got to do 1 centimeter times 1 centimeter times 1 centimeter equals, and then 10 to the minus 2 times 10 to the minus 2 times 10 to the minus 2 meters, okay? So you've just got to make sure that you're actually cubing stuff. Times 10 to the minus 2 centimeters times 10 to the minus 2 centimeters. I didn't put that in parentheses, but whatever. Okay, so our actual conversion factor is going to be 10 to the power of minus 2 cubed. So that is going to be 10 to the power of minus 1, 2, 3, 4, 5, 6. Okay. I knew that. 10 to the power of minus 6 centimeters cubed. Okay. So you just got to be super careful with that. Okay. I meant to write meters, not centimeters. Sorry, I have been very unwell this week, so I've got a bit of brain fog still. Okay, so that is your correct conversion factor. That 1 centimeter cubed is 10 to the power of minus 6 meters cubed. Okay, so just be careful. It's not 10 to the minus 2 meters cubed. You've got to cube both sides. Okay, so then I can take that 4.09 times 10 to the minus 4 centimeters cubed and actually convert it into meters cubed. So my volume equals 4.0409 times 10 to the minus, so 10 to the 4 centimeters cubed, and I want centimeters cubed on the bottom. So 1 centimeter cubed is 10 to the minus 6 meters cubed. So that is going to give me just 0.0409 meters cubed. And we haven't even like started the problem yet. Okay, we're just getting our ducks in a row. So that is going to be my volume. Okay, so my pressure is in pascals. No, it's not. It's in megapascals. Mega is 10 to the plus 6. So pressure 7.20 megapascals. So we're going to want to convert that. Hello. 1 mega. Give me a mega. Pascals is 10 to the power of 6 normal pascals. Just more mega. Okay. So then that is going to give me my answer for my pressure in pascals. So we've got pressure, we've got volume, we are solving for temperature, so we need our number of moles, and we've been given 2.30 kilograms of dinitrogen monoxide gas. So not only have we been given the mass in kilograms, we've got to work out the molar mass ourselves. So our number of moles, we're going to convert that kilograms into grams. So there's 1,000 grams in a kilogram. So 1 kilogram is 10 to the power of 3 grams. Whew. So that's going to give us our mass in grams. Our molar mass, I'm just going to stick it straight in. We're going to want to divide by our molar mass. Our molar mass is an equivalency every 1 mole of N2O. Nitrogen's 14 times 2, 28 plus oxygen, which is 16. So 38 plus, no, it's like 44 point something, right? So that's going to be 44.0123 grams for every 1 mole of nitrogen, dinitrogen monoxide. Okay, so that is going to give me my number of moles, which is 2.3 times 10 to the power of minus 3 divided by 44.0123 gives me, lots of small stuff for the number of moles. No, did I type in 10 to the minus 3? I think I did, right? 2.3 times 10 to the power of 3 divided by 44.0123. Should be big, right? Divided by, come on, calculator, 44.0123. Better, much more what I was expecting. 52.258. I'll just keep a few sig figs for a second. So we've got to rearrange the ideal gas equation and solve for T, and the temperature is going to come out in kelvins. And I've just looked at the question and it said it wants the answer in Celsius. Like literally everything in this equation we have had to convert. So T equals PV over NR. So do not forget, if our pressure is in Pascal, so 7.20 times 10 to the power of 6 pascals, the SI unit of pascals is kilogram meters to the minus 1, seconds to the minus 2. All right. And then get me a bigger box. Our volume is in meters cubed. We're going with this. It's going to be cool. So our volume is 0.0409 meters cubed, and then divide by our number of moles, which was 52.258 moles, times our times our gas constant. We're going to use the 8.314 joules per mole per Kelvin. A joule is kilogram meters squared per second squared per mole per Kelvin. Okay, so I know the units look a mess, but I really want you to be using your dimensional analysis so you can see that the moles are going to cancel out. My kilograms are going to cancel out, but I've hit an M instead of a K. Sorry. How did I even do that? That's supposed to say kilograms here. Kilograms, right? I'm going to cancel out. I should really look at the keyboard while I'm typing, right? Meters to the -1 times meters to the +3 is meters squared. So that is going to cancel out with this meter squared. And seconds to the -2 is going to cancel out, which leaves me with, where has it gone? 1 over Kelvin to the -1, which is going to be Kelvin. So it's going to give me a temperature in Kelvin, which is great because that's what we want. So 7.2 times 10 to the power of 6. Okay. Times 0.0409 divided by 52.258 times 8.314. Please give me a good number. It's like 677.7866 blah 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 Kelvin. Okay, so to convert that to temperature in degrees Celsius, we have to subtract the magic number of 273.15. So minus 273.15 gives me about 400-ish degrees Celsius. Okay, so that seems to be about right. Okay, so that's like that's probably the hardest possible question Alex could possibly ask about that. So most of the time you're just going to be using 0.08206 liter atmospheres per mole per Kelvin because you're going to have pressure in atmospheres, volume in liters. Occasionally you might have to use the 8.314 joules per mole per Kelvin when you have temperature in pascals and volume in meters cubed. And we have literally done all the unit conversions. Watch out for volumes. Watch out if you have to calculate your own volume and you've been given the diameter and you need to use the radius, etc. All right, so just be careful, write down your workings. Dimensional analysis is always your friend.